Hello, this is Mr. Kingsbury, and I thought I would add my own little piece of video here to what you guys are already seeing. We're talking about logarithms. I got to be honest with you, usually when I teach logarithms, I teach it at the same time that I teach exponents. So you're going to see me throw a little bit of exponential stuff in here. Truthfully, the two families of functions are very, 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 very close, very related. It's almost like they're two branches of the same function, same family, excuse me. They really go together so very well. And truthfully, one undoes the other, which we'll get to later here in a little bit. Right now, though, let's just start with what the pieces are. So let's start with what an exponential is. An exponential function is a way to quickly take a number and multiply it by itself a whole bunch of times, and then you get some sort of result. You may have heard about this in previous grades or what have you, when you see something like, for example, 3 times 3 equals 9, and then maybe you had a teacher that said, oh, by the way, we could write that as 3 squared equals 9. So you have this piece, this 2, that is an exponent, right? So this is our exponent right here. We call this number that's being multiplied by itself a bunch of times the base. And then this over here, you can either call that the answer, or more often, and this is a weird name, I don't know where it comes from, but we call it the argument. I have no idea why we call it that. I wasn't there when the Greeks came up with this stuff. I just teach it, but that's what we call it. Now, what happens is we can write stuff in this fashion, right? 3 squared equals 9. We're raising a number to another number, and we get a number. And of course, we're not going to leave it that way. We're going to put a variable in there, because what fun would it be without a variable, right? Right. You know I'm right. Anyway, what happens, though, is when the mathematicians of history started to try and figure out how to solve these things, they had to come up with ways to solve different possibilities here. And I don't know that I'm saying that well. What I mean is, when you start to put a variable in here, it could take one of 3 different places, and we got to figure out how to solve for that variable in each of those places. So, for example, if you've got 3 squared and it equals x, well, this was easy. You just raise 3 to the second power and you get x. So that wasn't too difficult. If you have 3 and you're raising it to the x power, whoops, we'll come back to that. If you have something and you're raising it to the second power and it equals 9, well, that's where square roots came from. And there's a kind of a long explanation about that. There's an algorithm you can use. We now have calculators that can do that for us. Certainly you can use an online calculator to help yourself out. Ultimately, the answer to this was to take a root, right? If you're raising something to a second root power, you take a second root. If I had, say, x to the 4th or 5th power, let's say, equaled something like, say, 32, I could take the 5th root of each side, and that would give me whatever my x value was. It doesn't matter what it is. It's just an example. It happens to be 2, just FYI. And then we came to this other issue, and that is what happens when the variable is the exponent. What do we do here in this situation? And to be honest with you, I don't know the whole process, how it came about, but ultimately this led to logs or logarithms. Someone came up with some way to take this and rearrange it so that you could plug in the 2 numbers you do have and get this x. And so you get something that looks like this. The log base 3 of 9 equals x. Or if we go back to our original problem up here, we could say that the log base 3 of 9 equals 2. And I know in the other video that you were given that you're watching, you have something that goes over this. I'm kind of going over it again. I'm going to give you my take on things a little bit, maybe explain it a little different. Hopefully that will help. I'll try and keep this short, but you guys know I'm not well known for my brevity. Anyway, this is x saying, what exponent would I have to raise 3 to get 9? Now, we're not going to talk about exponential functions. We're going to focus on just the logs. There's a way to do this using some of the skills I'm about to teach you that will allow you to solve for it instead of the method I'm about to show you. But the real easy way to do this is to figure something out like this is take your base, which is the number you're multiplying by itself, and start multiplying it by itself until you get the number that you're looking for, and then count how many there are. So let me give you an example. Oh, and before I do that, let me just label some things since I'm throwing around some vocab. Here is the base. This is the argument. And once again, we have our exponent or power. So those three pieces up here, they exist down here as well. I think in the video that you're given with the slide deck, they call this, instead of the exponent, they call it the answer. Because you can write the logarithmic form or the exponential form, and in the exponential form, it's technically an exponent. I like to just call it an exponent. We'll talk about converting between them here in a second. All right. So let me just give you a couple of examples. Example 1. Let's say I wanted to know what the log base 4 of 64 is. I have no idea. So the method we're going to show you is you take 4 and you start multiplying it by itself until you get 64. I could just write 4. That's kind of boring. You're not really multiplying by anything. If we did 4 times 4, that would be 16, right? 4 times 4, that would be, I'm sorry, let's do 4 times 4 times 4. We know 4 times 4 is 16, and we would multiply that by 4, and that gives us 64. So look, 4 times 4 times 4 gives us 64. That's 3 of them. Therefore, x equals 3. We're saying if you multiply 4 by itself 3 times, you get 64. That's what logarithms are, essentially. Now, there's more to it, and we can get into that later. Maybe you'll see it a little bit next year if you take pre-cal. But for now, for our purposes, this is more than enough. Let me give you another example of just how this works. What if we said we had the log base 3 of 243? I know that seems like a big number, but trust me on this, and it equals x. Well, 3 times 3 is 9. 3 times 3 times 3, that would be, this is 9, right? That would be 9 times 3, which is 27. Still not there. So then we'd have 3 times 3 times 3 times 3. So that would be 27 times 3, which is 81. Still not there. Then we have 3 times 3 times 3 times 3 times 3. That would be 81 times 3, which is, notice I'm just taking the previous number and multiplying it by 3 again, is 243, which is what we're looking for. So that's 1, 2, 3, 4, 5. 5 of them. So the log base 3 of 243 would be 5. And that's pretty much how you're going to work that through most of your problems. If you just take whatever this base is and start multiplying it until you get the number that you need, you should be good to go. There are a couple of other things that you should be aware about, and I want to, or aware of, excuse me, and I want to talk about those really quick. I have a way to present this that I'm kind of proud of, so hopefully this will make sense. For starters, you may have noticed that I was multiplying numbers by themselves, right? And that forms kind of a pattern, right? So I started with 3 squared, that was 9. 3 cubed, that was 27. I don't think we got, did we get 3 to the 4th? We did. 3 to the 4th was 81, and we got 3 to the 5th was 243, and I could keep going. And what I was doing when I went to the right was I was multiplying by 3, right? So I would take each one and multiply by 3. 9 times 3 is 27. 27 times 3 is 81. 81 times 3 is 243. The bigger the exponent gets, the more I'm multiplying by 3. The opposite of multiplication, though, is division. So if you start to work to the left, what you are doing is dividing by 3. So 243 divided by 3 is 81. 81 divided by 3 is 27, and so forth. 27 divided by 3 gives me 9. And here's the thing, if you keep doing that, you'll get more numbers. 9 divided by 3 is 3. 3 divided by 3 is 1, right? 3 divided by 3 equals 1. If you have 3 people, how many groups of 3 can you make? 1. And what's 1 divided by 3? That would be 1/3. And 1/3 divided by 3, if you'd like to see the math on that, I'll show you right over here. 1/3 divided by 3. That's the same as 1/3 divided by 3 over 1. Remember, when we divide fractions, we got to make them all fractions before we can actually do the operation. And we don't divide fractions straight up. We multiply by the reciprocal. So instead of dividing by 3 over 1, I will multiply by 1 over 3. 1 times 1 is 1. 3 times 3 is 9. So I get 1/9. And if I were to keep going, I would get 1/27th and so forth. Okay, now I'm telling you this because there's a point. Now, I'm following the pattern here. I'm ignoring the up top here. I'm following the pattern, right? If I go to the right, I'm multiplying by 3. So it'll get bigger and bigger. If I go to the left, I'm dividing by 3. So it's going to get smaller and smaller and smaller. So these are the values. These are the, if you will, the powers of 3, right? And I used that word because what we're doing is finding all of the things or all of the results of multiplying. I'm not saying that correctly. Let me try it again. What we're finding is what happens when we raise 3 to different exponents. And to start out with, it's pretty straightforward. But when you start to look at other exponents, negative ones, fractional ones, it becomes harder to do. And that's when you rely on a pattern like this. So here's the next thing I'm going to do. I'm going to look back up here where I started. 3 squared, 3 to the third, 3 to the fourth, 3 to the fifth. My pattern here is as I was going to the right, I was adding 1 to the exponent each time. Well, on the bottom, or when I go to the left, you can see on the bottom here, I'm dividing by 3. That means that I'm subtracting from each exponent, which means that if I were to continue the pattern to the left, the next one in the pattern would be 2 minus 1, which is 1. So 3 to the first would be 3. And if I did that again, I'd have 3 to the 0 power. 1 minus 1 is 0. 0 minus 1 is negative 1, right? And negative 1 minus 1 is negative 2. So now I start to have these negative exponents. So going to the right, we have these nice positive exponents. Going to the left, we start to get negative exponents. I would point out something also. If you'll notice my values here, see how this is 1 over 9? Well, remember how 9 is 3 squared? Well, wouldn't this just be 1 over 3 squared? And that's hard to see, so let me rewrite it. 1 over 3 squared, right? 1 over 9 would be like 1 over 3 squared, which means 3 to the negative 2 power is the same as 1 over 3 to the positive 2 power. You're not going to really need to rely on that. You don't really need to think about it all that much. I wouldn't. I would store that away, though, as kind of a piece of information to have for later when we talk about exponential functions and stuff. Mostly, I'm showing this to you so you can see where we get these fractional things. You're going to run into problems where we ask you something like this. We say the log base 2 of 1/16 equals, and you're going to be like, I don't know how to do that, because I can't just go 2 times 2 times 2. This is a number that's getting larger and larger and larger, right? What you can do, though, is focus on this. That was my cat, Scout. He says hi. What you can do is focus on this bottom number. 2 times 2 times 2 times 2 is 16. That's 4, right? So this would be like asking, what's the log base 2 of 1 over 2 to the 4th? Well, what is that? Well, if you'll remember, this can be written with a negative exponent. So you could say something like the log base 2. So 1 over 2 to the 4th would be like 2 to the negative 4th equals x, right? So then 2 to what power? I feel like I'm getting really, really complicated here, and I'm making it more confusing. So I apologize. I was just trying to figure out a way to tell you or to show you how to find these fractional ones that may make sense. My point is that a negative exponent gives you this fraction, and you can find what that exponent is if you just focus on the bottom number here. 16 to the 4th power, or I'm sorry, 2 to the 4th power is 16. And because it's a fraction, you know that it's a negative thing. Anyway, I just thought I would share that with you a little bit. For the most part, you won't have to worry about it. You can just use that multiply it kind of process, and that will get you where you need to go. The other thing that we were looking at was converting between the two forms. Okay, so generally speaking, you have your exponential form, and I'll just use variables to represent everything. So we've got our base, which we'll call b. We'll raise that to some sort of exponent, which we'll call a, and that will give us the argument, which we'll call c, right? Base, exponent, sorry, it's not a t, it's an n, exponent. It's not expotent, it's exponent. And then we call that the argument. And then with your logarithm form, you have the same three pieces, they just get organized. You always, or reorganized, I should say. You always start with the word log, and actually you'll note in both of them the base comes first. B would come here. What happens is basically the exponent and the argument kind of switch. And I'm going to talk about a method here in just a second. But what happens is the C goes inside the parentheses here, and then it equals the A. The argument goes in here. Did I call it the argument? Yeah, the argument goes in here, and then the exponent is out over here. I've seen a method, hopefully this works for you. It's called the circle method or the wheel method, something like that. The idea is when you're going from one to the other, you can just kind of follow it in a circle, right? So if I'm converting a logarithm to an exponent, you always start with the base, and then you go clockwise, right? Like that. So you would go base raised to this exponent equals this, right? See how you go across the equals and then back base to this equals this. And the same goes for the logarithm. When you are rewriting it as a logarithm, you always start with the base, and you go the log base this of C, or of the argument, equals the A. So once again, that equals, you go across at the end there, that's what you end up equaling, right? So B log base B of C equals A, which that probably just sounded like a bunch of gibberish. So how would I show you some examples instead? Let's say I did the log base 2 of X equals 16. And I wanted to rewrite that as an exponent, or in exponential form, right? So I'll start with the base. I will go across the equal sign and then back across the equal sign. So what does that look like? I start with the base 2. I raise it to the power of 16. And that will equal whatever is in here, my argument in this case, x. Let me do another one for you. The log, I guess these are examples, so I can call them examples 1 and 2. A little messy, sorry there. So let's say the log base 7 of 49. No, let's raise it a little bit more. Let's say 343 equals x. If I wanted to write that in exponential form, I always start with the base, 7, raised to the power of x equals 343. And the other way works as well. I don't know that you're going to have to convert it, but I'll show you a couple just to be on the safe side. So if I had, say, 4 to the x power was equal to 256, you could write this or rewrite it in log form. First of all, you write the word log. You start with your base, which is 4. I would open parentheses, and then you will take the log base 4 of this number, 256, the argument, and that's equal. Log base 4 of this number is equal to x. Whoops, I messed that up. How about equals x? Something like that. Let me do one more here for you. So what if we had, say, 3 to the 5th power equals x, and we're going to rewrite it as a log. Yeah, so you would start with the base, right? So it'll be log base 3 of x equals 5. It's just in a circle clockwise every time. So that's how you rewrite it. Don't overthink it. I find a couple things to be true on this. The first one is students have a tendency to overthink this. They really overthink it way too much, and you don't need to. Okay, you're just multiplying things, the same thing over and over. Not a big deal. Also, when you're converting stuff, you always start with the base and pay close attention to what you're converting to. One of the biggest issues that I see, I'll just give you an example here. Particularly when students are converting some sort of exponential, like say 2 to the x equals 64, they'll follow the circle thing, and then what they'll write is 2 to the 64 equals x, which is wrong. This is wrong. This is not good. Don't do this. This doesn't have the word log in it, so you didn't write a logarithm. You wrote another exponential, and all you did was switch the power or the exponent and the argument. That's all you did. You didn't write things that are equivalent. You wrote another exponential instead of a logarithm based on this exponential. I don't find that to be the case as much with logs. People are usually good at dropping the log. It's remembering to write it that is a problem. The other thing I wanted to point out, and I want to go back to my example here, is when you look at the powers that we wrote out here, you'll notice that 3 to the first power gave us the number 3. 3 to the 0 power gave us the number 1. There's a couple hard and fast rules in there. Anything to the first power is itself, right? So I'll just throw down here really quick. So 4 to the first power is 4. 10 to the first power is 10. 137 to the first power is 137. The other hard and fast rule, and this is more important than that, the one I just showed you, anything to the 0 power is 1. 5 to the 0 power is 1. 8 to the 0 power is 1. 23 to the 0 power is 1. 764, I don't know, to the 0 power is 1. It doesn't matter what the number is. If you raise it to the 0 power, you get 1 every time, which means if you're taking the logarithm of something, doesn't matter what the base is. If you're taking the logarithm of something, any base, and you're taking the log of 1, it's always going to equal 0. Just something to keep in mind in the back of your head there. I hope that doesn't mess you up too much. I do hope those examples help a little bit. I would say the best advice I can give you is when you are finding a log, start with the base. Start multiplying it until you get what you're looking for. Or if they give you one, I didn't think about this, and I don't know that I saw any of these, but I'll throw it out there. If you are given a log with some base, and they tell you it equals something, so in this case, instead of trying to figure out how many times, that's not good. Let's do this. Sorry, messed myself up. In this case, what they're asking is how many. What happens when you multiply 3 by itself 4 times? That's what this says, and they want to know what do you get. This is really 3 to the 4th power equals what? That's what this is really saying. I don't know that you're going to get any like this. I'm pretty sure that they're not going to give you any like this. They're going to be like what I did before, where you have these two numbers and you just got to figure that out. We're trying to keep it fairly basic. We know that you are at home and you have limited contact with us, so we're trying to make it pretty palatable for you. Anyway, if you've got questions, do not hesitate to email myself, Miss Daughter, Miss Motes, or Miss Loftus. We're more than happy to help you. We're glad to be of service. We're monitoring pretty much all day, every day for your emails and stuff. So good luck, and I will see you later.